Let's talk about Romberg's method, the theorem. The theorem is the basis of the application. So what is Romberg's fantastic theorem? We go back to the trapezoidal rule, the most simple idea to do numerical integration, and then t of h, we have a function, we have an interval, and then t of h is the trapezoidal value if we work with the step size h. So for example, if we integrate from 2 to 3 and we choose h to be 0.1, then we have 11 evaluation points, the 2, the first, the 11th one, the 3, and then we get a trapezoidal value, and then t of 0.1 will be that trapezoidal value. And we can write that to be the exact value plus an error term. We will not know the exact value, and so we cannot know the error term. But this is a great idea, as we will see. We can write this error term as a Taylor series, okay? A Taylor series, that's a great idea. And now the absolute value is 0, that's clear, because if h tends to 0, then the Taylor series gets more accurate and more accurate. That's what we learned about the Taylor series. And then normally there will be c1 times h, and there will be a c3 times h cubed, and there will be a c5 times h to the power of 5. And these are missing, the odd potencies are missing. And by applying that, our idea we will get even more powerful. It's not really necessary for the idea of Romberg that these are missing, but this increases the accuracy a lot. Okay, so this is only true if f is differentiable often enough. Okay, I don't want to write that. And this is a very crucial or very powerful thing here. Okay, and what's about these numbers? The numbers here, C2, C4, C6, depend naturally on A, on B, and on f of x, but don't depend on h. That's clear because if we write as a Taylor series, that is natural clear. Okay, we will not find out which are these parameters. We will not find their value. That is of no interest at all. And surprising, we can take a benefit even if we don't know these coefficients. And what is the situation here? We hope that this is a small number, because that means that our trapezoidal value is very close to the correct value. So this is our hope. This shall be a small number. Okay, what does that mean? If we hope that this is a small number, which part of this sum matters? This one is the most important one. Why? Let's assume that this is the error term. Then what will happen? If we use h to be 1 divided by 100, then we get 0.2 times 1 divided by 100 squared. This is 1 divided by 10,000, and this is 10 to the power of minus 4, and so we get 2 times 10 to the power of minus 5. Here we get 10 to the power of minus 8, and so we get, and here we get, h is 10 to the power of minus 2, so we get 10 to the power of minus 12, and so 3 times 10 to the power of minus 13. And that means what? It means that all parts are very small, but this one is nothing compared to that, and this one is even less than that. So this contribution is more or less nothing. It doesn't matter because only this number matters. So, and now comes the great idea of Romberg, which started with that And now let's use that, and instead of an h, here is an h halved. So we have c2 times h halved squared plus c4 times h halved to the power of 4 and c6 times and so on. And now we can write that as h squared divided by 4. Let's take that here. So a quarter c2 plus here it's 16. 2 to the power of 4 is 16. So 1 divided by 16 c4h4 plus and so on. And now remember, what do we do if we have a system of linear or nonlinear equations? Now we can add these two, and what will happen? So we want to cancel this here. And how do we do? 4 times that minus that. 4 times that minus that will be 3f. We want to have a f. So we do 4 times that minus that divided by 3. And what do we get? 4 times f minus f is 3 times f divided by 3. This is an f. That's what we want. And now 4 times that minus that is gone. There is no h squared. And that's the great idea, because the lowest potency matters. And if we can cancel h squared, then we will have only h to the power of 4, and that's much better. So here 4 times that minus that is nothing, divided by 3 is nothing. 4 times that is a quarter, minus that is minus 3 quarters, divided by 3 is minus 1 quarter. Minus 1 quarter c4 times h to the power of 4, and here something with h to the power of 6, and we can write that to be this way. This is terms at least power of 6 or more. And so now we cancel this h squared, and here we have a quarter instead of a 1, minus doesn't matter. So this is also an improvement, so very, very good. And so that's the great idea. And let's understand that idea by having an example. Let's talk about the function e to the power of sine x, 3 times sine x, and let's integrate from 2 to 3. And if we are interested in that value, we apply the trapezoidal rule. Let's choose an initial h. Which initial h shall we use? Let's say we start with h is a half. This is not important which h we use. For this example, we use h is a half. You can also use h is a tenth or whatever. Okay, then we need a tabular of x and the corresponding function values. And in this example, the first point is 2, the second point is 2.5, and the third point is 3. Now we have to evaluate e to the power of 3 times sine of 2, and using electronic help, it will tell us 15.301. Here we get, and now we get the trapezoidal value for a half. This is our h. The initial h is a half, and so we get this difference here, a half times, and then a half times the first value plus this value. And then here's the last value, so this one again times a half. And using electronic help, you will get the value 7.218. Okay, this is our trapezoidal value for our initial h. And now let's find our trapezoidal value for half of that initial h, so it's a quarter. And then this tabular is a little longer. And we get the values, and in between, using electronic help, we get we get these values. And now our trapezoidal value is a quarter, this difference here, a quarter times first value halved, plus these values, plus the last value halved. And we get, and now we have these two values, and now we can calculate that value. We can very easily calculate that value. We only have to do 4 times the better value, this one, minus 1 times the first value, this is that, divided by 3, and using electronic help we will get 6.8939. Internally I used more digits. I'm not sure if you get a 9 if you do exactly that calculation. Internally I used a lot more digits. Okay, this is our improved value, hopefully our most likely improved value. So let's check what is the correct integral value. We can get this value by asking Octave, the quad command, or we can get it by a very high refined here tabular, and then we apply trapezoidal or Simpson or whatever. And the correct value is 6.8981. And so let's check, we are very close. The first 2 digits after the decimal point are correct. And here they were not. So with the help of these 2 values, we can get a much better value. And that is kind of miracle. At least for me, this is kind of miracle. Because we use a rough approximation of the correct value, and only on the basis of these rough values we can get a much better, a highly improved version. And normally if you mix 2 things which are not very good, then the mixture will not be better, but in this case it will. Okay, so this is the idea of Romberg, and it works. And in the next video we will even refine that idea, because then we will add a 3rd trapezoidal value, and then we can even get rid of h to the power of 4, but that's the topic of the next video. Okay, this was our video about Romberg's method, and in the next video I will show you how it applies if we have more stages than only 2.